Nice to have that wind die. That wind makes me irritable. Administratively, those of you who were sort of stuck with being able to get a hold of me have pretty much picked almost unanimously 8 o'clock in the morning on Thursday. Sorry about that. 8 o'clock is shocking to my system, but I'll do it. I will, because it's more about you getting access. It's about what can you make more than what is convenient to me. So 8 o'clock, come to my office. I'll start this Thursday. Remember, many of you are using the Thursday noon hour, so I have 2 different reviews on Thursday for you, and I'm happy to do that. By the way, if no one shows up at 8, I will just go back to bed on the couch in my office. But I will try it for a while and see how you guys do. Usually you guys are more reliable than I am. So last time we were talking about, we talked about, as a protracted example, how the recruitment, how do you get 20 times the use of glucose compared to rest during exercise? And we talked about multiple steps. Neuroendocrines help with the breakdown of glycogen, flooding the blood, and breaking down the glycogen granule muscle. Then we saw that the enzymes become hyperactivated. They drop their KMs due to both covalent and allosteric mechanisms. And towards the end, we saw that there are adaptations if one repeats the exercise bout that expand both the muscle's capacity for glycogen storage. We haven't talked about hormone adaptation, but you do adapt and have more epinephrine available. So the entire system, you have more mitochondria installed in and so ultimately the entire system, it's like your lawnmower, the more you use it, the more horsepower it adds. It's really quite strange. In an automotive model, it doesn't make sense. In a biological model, it's very common. So today, we're actually going to begin talking in detail about the metabolic pathways that replace ATP. We will talk a little bit in detail about ATP because it is the coin of the realm. It is the best tool for running biochemical reactions. So bioenergetics is the conversion of small molecules into one another and harvesting the energy in the carbon-carbon bonds into usually ATP. We're going to talk a little about ATP. Muscle hardly uses any at rest. Boy, it can go up over 200% rate of usage. So this is per minute, this is per second. So you can have a huge increase in the rate that its muscle is using the ATP. If we talk about bioenergetics, I think I just said that, what it is. ATP is our metabolic currency. Let's see. Remember that if we use catabolic, we break down long carbon-carbon chains to release the energy therein to drive an endergonic reaction that takes ATP up to high energy. And then this ATP is very, very handy for the synthetic function, the anabolic function, for synthesizing large molecules. You can also use the ATP energy for a lot of other things that I'll remind you of. So let's see here. 1, 2, 3, 4, 5. We're talking about at least 5 different pathways by which you can regenerate ATP. And the fact that there are multiple pathways is probably one of the biggest keys. We don't just have one engine. We have multiple engines in each cell. And the combination is stronger. It's sort of like if you had a basketball team where everyone is exactly the same height, right? If they were all big men, as we say, you would be devastated by fast break 3-point shooters, the team that came against you, right? And if they were all little 3-point shooters, you'd be devastated in rebounds. And so by having a basketball team that's made up of 5 different quality players in terms of stature and abilities, you have a stronger combination. That's a pretty good analogy for ATP regeneration. So for each pathway that we're going to talk about, and boy, this area really lends itself to flashcards. You want to, why do you have this pathway? What circumstances make it go faster? yeah, these are related. Rate control. What is the substrate of each pathway, and what do you get out at the end of each pathway? For instance, today we'll see that, well, tomorrow we'll start to talk about glycolysis in detail, and taking the glucose as a substrate, and coming out with pyruvates at the end. There's more than one advantage. You got 3 ATP just from the breaking of the carbon-carbon bond in glucose from a 6 carbon into 2 3 carbons. So you've got some energy. But even better, your pyruvates can be submitted to the mitochondria, and you can get tons more energy. So often there's multiple reasons for why a pathway exists. I've mentioned that if metabolism is about breaking down macronutrients, the macronutrients are what we put in our mouth: carbohydrate, fat, protein. And these are digested both in the GI system and then digested at the cellular level to harvest their energy of their carbon-carbon bonds to make ATP. And then we can do all kinds of physiologic things. I think the next slide shows examples of what you can do with an ATP. Important to remember that here's a list. Here's a list of, by body weight, in an average 65, 70 kilo person, how much of us is made up of these things. So proteins, about 45 pounds, 50 pounds. I want to point out a lot of this you cannot lose. I mean, you can lose 20 pounds of protein, you'll be skinny and sickly, but a lot of this is essential. The same is true of fat. Humans have an obligate level of fat. For males, it's around 6%. For females, it's around 12%. And if you don't have it, it means your gonads don't function, your brain gets messed up because it's mostly fat. All kinds of dysfunctions occur. All plasma membranes are made of fat, right? Like phospholipids. The reason I put a star here is to point out, what did we say the preferences, if you're working at very high intensity, what is the preferred fuel? What do we have the least of? Yeah, so this becomes important. If you're lucky, you may have a kilo, 2.2 pounds. All right, what's this? Oh, this is just showing, oh, good for me. I said gut, so here's digestive absorption, and here's cellular level catabolism, where you actually break down. And remember, superCoA is key because it's the entry molecule. When combined with a malonyl-CoA, I think you get a citrate fairly soon after that. And the spinning around of these citric acid moieties both yields ATP directly, and then you can pass on the reduced coenzymes, NADH and FADH2, to harvest energy in the electron transport chain. All review, hopefully? So, how much energy is in each of these foodstuffs? The way you would do that is burn, literally burn, oxidize in a physical manner the foodstuff down to its constituents, and you do that in a hyper-insulated container so you can measure the total heat release. And so this would be the equivalent of the enthalpy. Remember, enthalpy refers to the total heat available inside the beast. So remember, I think you guys quoted these numbers to me early in the class. I tend to forget them. So carbohydrate gives you roughly 4 kilocalories per gram. Remember, because lipids are more reduced to begin with, right? On a carbohydrate, there's already a lot of oxygens. But in lipid, it's almost all carbon, 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 HH, proton, proton. And so you get much more energy per gram of fat. And then proteins are intermediate. Remember, we don't use protein as a primary oxidative fuel unless we're forced to by either a single protracted work bout, 3 hours or more, or starvation will cause us to use protein. For the most part, protein is reserved for structure. Does that all make sense? Does anyone know what alcohol is? It's about 7. About 7. But you're right, Salvador. It's more like salad oil than you know. So if you take a shot, it's salad oil. Just something to remember. You know, a single beer, I once calculated a 6-pack is 300, it's like almost 1,000 calories.
What kind of beer are you drinking?
Good beer, and I don't drink a 6-pack anymore. 6-pack lasts me.
Most of our Coors Light.
That's water, that's not beer. So, a strange form of demented water. So on to ATP. Adenosine triphosphate. Where is the adenosine? Oh, here's adenine. Here's adenine. Ribose bond. And then we got phosphate, phosphate, phosphate. And that's alpha, beta, and gamma. The gamma, there's slightly different energies for each of these phosphate bonds that I tend to lose track of. Let's see if we can find them. The gamma appears to give you a delta G, just breaking that last one, of 7.3 kilocalories. I think that's right. Then I start to get confused if you say, don't worry about that, because this is the most common reaction, to break the gamma bond and turn ATP into ADP. It's okay? Yay, this is what I wanted. This in the next slide will give us how, you know, I forget, I've been a student in a long time. Are quarters still really useful? I know now that we don't have meters anymore, parking meters, but quarters used to be just gold when you were a student because they ran the washing machines in the dorm, and then they were good for parking at a meter, and so it turned out you always needed quarters because they were the right size. The $20 bill was nice, it was nice to have 20 bucks, but you couldn't put it in a meter and you couldn't get your clothes clean. That's ATP. ATP is sort of the perfect packet of energy for getting stuff done. And so as the foodstuffs are digested down, cellular respiration, you can use the energy to create ATP. And the ATP is just the perfect packet. So I guess the total size of this gear is representing the Gibbs free energy. Again, good iconography means something. They aren't just pretty pictures. So this means how big is the delta G. Well, notice, you could have other reactions with slightly smaller. This could be pumping a potassium in and a sodium out at the membrane, right? And we can do that for 1 ATP. We could be pumping a calcium back into the sarcoplasmic reticulum of a muscle cell so that at rest we have nice relaxed muscles that aren't stuck in a cramp, right? We could, what else can you do? There's all sorts of things you can do, but you get the idea that this is sort of the perfect size to run reactions, and I think this shows it the way the biochemistry students will like this better. That here's your delta G's, here's ATP at about 7.3 for the tertiary gamma bond. Notice that it's intermediate between things that have a lot of energy. We'll talk about organ and phosphate in a moment. I believe that is an intermediate in the glycolysis cycle. And so you can harvest the energy in these and change it into ATP. Then the ATP can actually do things that you can trap a glucose inside the cell, hexokinase, right? You can do things with this ATP that make other useful functions. Okay. So we do maintain a homeostasis in this stuff, which is critical. There's a word for people who don't maintain ATP homeostasis. And that word is dead. Remember we said that at rest, muscle uses about 1 mole per minute. And so if you think about this, if this is our reserve, we have about 4 minutes until cell death starts. Again, it's right back to CPR. Why do you need to start CPR within the first 4 minutes? So the cells don't die. Start to transport oxygen into the cell. Muscle, what's really interesting is ATP homeostasis is so good. Remember we saw that you can use 200 times, so something like 100 times the total amount inside the tissue. You can be using it at 100 times that rate and not have the ATP concentration within the cell drop. Well, that's astonishing. It means you must be able to replace ATP remarkably quickly. So one way, so how do we capture the ATP concentrations in a cell? The best way to think about it is I will now use, you guys will always, what is a Dennelite charge? Even on the midterm, what is a Dennelite charge? Okay, I'm going to tell you right now. A Dennelite charge is the energy status of the cell, where a big number means there's lots of ATP. If you want to look at it mathematically, it's saying of all the adenosine moieties, the top part are the high energy moieties. ATP and ADP are both reasonably high energy. Right? Then down here, you're putting all the adenosine beasts below. So of the total adenosine you have, how much of it is being kept in the high energy state? And in normal critters at rest, the value is about 0.8. Now, even during the most intense exercise, it's very rare to see a value go much below 0.75. People who go down here are dying when energy levels start to go down. Someone in a heart attack will have a population of cells in their heart muscle whose adrenalate charge is below 0.6. Well, that's because they're going to be dead before the day is over. So it's kind of amazing how strong. Now, one of the reasons I'm bringing this up, and why don't we keep this at 1.0, partly because the world is not perfect, is one answer. But another answer is these low energy adenosine species are informational. And let's see if I can develop that idea. No, I guess not. Put that on the back burner for now. Oops, what's happening? That you don't want this to be 1 because you actually are using these lower energy moduli are actually signaling the enzymes, sort of like what we're wanting CO2 to do. These things are telling the enzymes, and how fast should we be making ATP? And so I'll give you an example, I think, by the end of the lecture. All right, so now we're ready to talk about resynthesizing ATP. Any questions about what I've said so far? Just sort of a big overview. ATP. You want some. Here are the 5 pathways we'll be discussing for the next 2 weeks. Today we're going to talk about the phosphagens, which means generators, gens, genetics, genes, genesis, of phosphate. And so these are stored high energy phosphate already in your cell. We'll talk about these today. Then we'll talk about glycolysis, where you actually start to break down carbohydrate. We'll first talk about cytosolic glycolysis, and then we'll spend about a week talking about mitochondrial oxidation of carbohydrate fat. Okay? So today we're talking about blah, 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 and then tomorrow we'll talk about blah, 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 and then next week we'll blah, 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 blah. This is an important graph that I'm going to show you. Do you know the word ad nauseum in Latin? I will show this to you until you're sick of it. It's showing you the number of kilocalories per minute of energy that can be released. And it's showing you from the phosphagen system, the anaerobic glycolysis or incomplete glycolysis in the cytosol system, and the oxidative functions of the mitochondria. Very important figure. It is showing you over the period of time, that's 30 seconds, 10 seconds is about there, 10 seconds, 30 seconds, 60 seconds, 2 minutes, 10 minutes. And it's assuming that for each of these time periods, the person is working as hard as they can. So you take a person, what's 30 seconds? That's longer than a 200. It's like a 300 meter. Run as hard as you can. What energy source do you use? I want you to notice back here before work starts, all of the energy systems are on board. You are using fat, you are using carbohydrate. Everyone in the room is making lactate right now. None of them turn on and off or are sequential. But notice that their output and their sustainability are different, and they're inversely related. The ATP storage, you can do ginormous amounts of work. Unfortunately, your ATP only lasts for about 3 seconds, and your creatine phosphate might add 10 more seconds. So by the time you get 15 seconds, you're bust out of luck if you're hoping to use phosphagens as your energy source. Fortunately, a second system has come up, and it's not quite as high capacity as this one, but you can create lactate in your cell cytosol and come close, about half the energy Notice, as I said last time, that mitochondria are often late to the party. It depends on the workload. If this was an intense workload, it might take you 10 minutes to get to steady state. But usually in 2 minutes for a mild workload, you'll come up and stabilize. Does that all make sense? So inversely related, intensity and sustainability. Same figure down here. If I was going to circle something, I would circle this. It's showing you the maximum rate of ATP synthesis. And notice the systems we're going to talk about for the rest of the hour, ATP and creatine phosphate reactions, if you average these two, call that about 10. Well, that's at least 8 times faster than anything if this is 2. 10, 2, 5 times faster than anything the mitochondria can do in terms of ATP replacement. So if you want to do really intense work for short periods of time, is Richardson here? Oh, Jared, you're back. Good to see you. Jared, right? Yeah. Good to see you. I've been talking about you because there's biochemistry happening. And Greg Richardson is not here, but Greg, we're talking about discus throwing, and if you're on the home audience, if you're home alone, notice that ATP and creatine phosphate are basically where you live because your shot and discus leave your hands usually in less than 3 seconds. Right? You start to see different athletes have different desired attributes. Is this all making sense so far? Okay. Notice again, duration is over here. And so if you wanted to contrast, boy, this is great. Why don't I just always use these two? Well, because in 10 seconds you're done. And so there's a reciprocal relationship between these. You can read that on your own. It's just referring to the fact that different sporting events are kind of relying on different energy systems, and this is why they train differently and get different adaptations. Okay, let's talk about two different systems. Now, this is what's called substrate level phosphorylation. And this is one of these words that professors say to you, and you kind of go, what are you talking about? Substrate level means as opposed to phosphorylating something in the electron transport chain using ATP synthase. So as opposed to mitochondrial phosphorylation, substrate level phosphorylation is when there's a carbon moiety floating around that has a phosphate on it, and it's willing to share. Here, you can have my phosphate. Are you running low? And so that would be phosphate level here. This is what's just happened. I was a creatine molecule, creatine phosphate, and Adelaida had just dropped down from ATP to ADP. I immediately hand her a high energy phosphate in order to get her back up to full function. That make sense? That's what substrate level phosphorylation is. We have two systems that do this. Anaerobic glycolysis does it badly. We'll talk about that tomorrow. I want to talk about the phosphagen system today. I posted a little reading. It's a single page. It's by Gina Kolata, a Pulitzer Prize winning science writer for the New York Times. It's just a page, and I think the title of it is in your Canvas, and it's under a folder in the files that says reading. And it says, lactate is muscle's friend, not foe. And you can read that. It'd be good to read. Remember, this problem goes all the way back to 1917 and even before that yeast are what are called facultative anaerobes. If you take away the oxygen of yeast, then they start to use anaerobic system. That's not us. We will use the anaerobic system based on workload, not oxygen availability for the most part. So we do it all the time. It's better to call it non-mitochondrial ATP resynthesis rather than anaerobic. It's better to call this glycolysis cytosolic or incomplete glycolysis, or use the eponym, because we're not yeast. You may have noticed. All right. Phosphagens, we're talking about phosphagens. We're talking about high energy phosphate compounds, meaning ATP and creatine phosphate. Creatine phosphate, the phosphate actually has a delta G up around 12 to 14, so it's actually more energetic than here. It has to be in order to transfer that phosphate onto the gamma phosphate of ATP. These systems are, one of the reasons they're so incredibly fast, and this is a nice sort of take-home point about speed of if you have one enzyme, it is flickering whatever its reaction is. It's doing it in a millisecond or less. I don't know, you have to go measure it, but it's fast. If you have 10 enzymes in a row, each one waiting for the product of the enzyme in front of it, you start to add up those milliseconds, right? And so it gets longer and longer the longer the enzyme chain. So these phosphagen regeneration is fantastically fast because for the most part, they're using single enzyme reactions. The creatine kinase reaction and the adenylate kinase reaction, also called myokinase. So let's look at these two. Remember, at rest, the way where the ATP is going, if you're not doing myosin ATPase, you're using your sarcoplasmic reticulum and sodium potassium pumps to keep the electrolytes where they ought to be before all hell breaks loose. So creatine phosphate, let's see, something like 95% of the creatine phosphate in the body is found in skeletal muscle. So I think of it as a backup battery for ATP. If you're in a muscle has the potential to use up ATP rather quickly, and so you have a backup battery. You can read about it here, but it's everywhere that you use ATP. The concentration is 3 to 4 times that of ATP. So if you've got 3 seconds of ATP, 3 times 3, 9, yeah, good. You have something like 10 to 12 seconds of creatine phosphate to back it up. All making sense? And here's the reaction that does it. Here's creatine up here. I forget what you call a nitrogen. If the nitrogen is the central moiety and you've got carbons coming off it, does anyone remember the name of that? I don't. Nitro? No. But this is a creatine. This is creatine phosphate. The creatine kinase reaction will take an ADP. So here's your energy releasing function where ATP's been broken down by some form of ATPase. You've just pumped the sodium out and potassium in. Well, you want to replenish this right away. The fastest way to replenish it is to take that product as a substrate combined with high energy phosphocreatine. Creatine kinase then shifts the high energy phosphate back onto the gamma position, and you're left with naked creatine. Is that okay? That, and you're wondering how do you fix that naked creatine? You'll see there's a creatine phosphate shuttle that goes straight to the mitochondria to pick up a fresh phosphate from the mitochondria. But this is the fastest way to get back to function. The myokinase reaction is not nearly as important quantitatively. Most of the phosphagen replenishment comes from creatine kinase. In extreme situations, high intensity exercise, you'll tend to have a multiplicity of ADPs. They'll start to predominate as the adenylate charge. What does adenylate charge mean? The energy status of the cell. As the adenylate charge drops, there's going to be proportionally more ADP, and adenylate kinase is able to take 2 ADPs and combine them to get one high energy and one very low energy. Does anyone, again, the logic of this seems goofy, but what's happening is you've got one high energy that you can use right away, and what you'll find is that thing right there, that is the equivalent of a metabolic screen. That when AMP starts to appear in a cell, enzymes react, and they react strongly to fix the energy deficit. So myokinase is both doing a short-term provision to preserve current energy state, and it's saying, we need more metabolism. Mary?
Going back to the previous slide, is that why people take creatine?
Oh, we'll talk a little about creatine phosphate supplementation in just a second. It's a really good question. In fact, let me see where I am supposed to talk about that, because I know you're interested. Yeah, Molly. Oh, it's actually in 5 slides. Be brave. 5 slides? It's a great question. Oh, this is cool. This is a genuine Metabolic MRI. You know, you can do MRIs to visualize using Fourier analysis to get anatomic. But you can also use a metabolic MRI, and what you actually see are spikes of specific molecules, like on a grass chromatography. Yeah, you know what I mean. So this is a thigh that's sitting inside of an MRI tube. And then you say, okay, flex as hard as you can. You just, massive contraction. Notice what happens. These are the three moieties of ATP, gamma, alpha, beta. If you look here very carefully, time is going back into the board. Why are there these different lines? I can't remember, it's every second. 24 seconds, and I think there's 24 lines. So every second there's a reading on the metabolic status of the muscle. Notice, can you see that ATP drops in the second and fourth second? See how small the ATP changes are in a muscle? And yet, it's a maximal contraction. The muscle's using up ATP as quickly as it can. So how is it managing to stay constant at the gamma? What is this? This is the creatine phosphate. Notice it starts here before the contraction starts. In the second where the red is, the contraction starts. Whoa! That's got to be a 30 or 40% dip in the concentration of creatine phosphate. So creatine phosphate is acting as a resuscitative emergency battery, and as soon as one of these comes off, this is slapping a high energy phosphate back on. Does that make sense? Sir?
Is that entire graph the 24 seconds?
Yeah,
Or is only the red?
Oh, sorry, thank you. 10-minute recovery. 24 seconds here, which makes these about 3-second intervals. And then this is 10 minutes of recovery. Notice you don't need the entire 10 minutes. If we come across, as soon as the contraction stops, gosh, within 10 seconds, you've resuscitated your creatine phosphate. Maybe 12. Everyone tracking that? Thank you for that. What was your name?
Moses.
You're Moses. 8 o'clock. Everyone follow that? This data is rare as hen's teeth to actually see genuine molecular change in a working muscle of a human. So this is So this is a summary from an earlier study, same outcome of doing 30 seconds of maximal leg cycling. And then they biopsied and froze the sample instantly to see what had happened. So they biopsied before and then the instant that exercise ends. And what you see is, let's first go to ADP. The maximal 30 seconds, ATP does drop. You'll find that's about a 10% drop, right? From 0.8 adenylate charge to 0.75, right? So what dropped a lot? Well, creatine phosphate went down the toilet to keep that stable. Free creatine went up because you took away its phosphate. Inorganic phosphate is your biggest percentage change, and we don't have AMP on here, which is a shame, but AMP will be. Is that making sense? Now, what I was going to say about information, this is like people who study informatics, you know, where is the meaning in systems? Let me show you what's happening in the adenylate charge. And I generated these data from real studies. I took like 3 or 4 real studies like the ones we just saw, and I generated I did it in total number of molecules because that's easier for an undergrad to see. So we got something like 9,400 adenosine moieties of all different kinds. And at rest, of course, the vast majority of them are kept as ADP, and that gives you an adenylate charge like that. By the way, this is telling the cell how fast do I have to keep up. It signals the enzymes to keep stable. Now notice when you begin to become active, there is a drop in ATP. It tends to be remarkably tiny, right? So if you're going to key enzyme allosterically to activate at something like ADP, well, that's kind of a crappy signal. You know what I mean? 5% within the noise, it's like the enzyme's barely going to see it. What if the enzyme is allosterically sensitive to AMP? Boom! Or allosterically sensitive to inorganic phosphate, which may go up by 400%. And so from an informational level, this is why evolution has targeted so many of the molecules in the energetic pathway to focus on inorganic phosphate, calcium, and AMP. Does that make sense to you? It's informationally, that's where your biggest signal to noise ratio is. Okay, yay, good for you. A little technical thing. So when we look at our phosphagen system, and this is going to be very similar to what we saw before. I use a lot of different sources to sort of convince you that I'm not making this up. This is in the data. That, I wish they had seconds. We don't have seconds here. It shows the same basic relation that you have perhaps 4 times as much high energy phosphate in creatine as you do in ATP, and you can go through it. So, on to creatine, to Mary's question. So, I think I want to start by asking you questions first to see if you've understood this. So let's pretend, and this is usually not true, but let's pretend that someone doesn't have enough creatine in their muscles. Which phase of exercise are you going to see the biggest problem in this? Yes, exercise bouts lasting less than 15 seconds. So now I want you to just make a guess based on your knowledge in this class so far. Would creatine phosphate supplementation help a marathon runner? No. What would help a marathon runner is to warm up, get their mitochondria ready to go, and forget about creatine phosphate. And indeed, that study's been done multiple times. Creatine phosphate does not improve aerobic performance, right? Then the issue, again, what I'm trying to teach you is fitness and performance does not come from what you put in your mouth. It really doesn't. Fitness and performance comes from what your muscles do, repeatedly. So I'm not against putting things in your mouth. I put whole foods in my mouth nearly every day, along with fluid. But that's not what's making the change. So I want to remind you that when you go to GNC and look at this stuff, the vast majority of it never makes, that you put in your mouth, never makes it to the target tissue. They will sell you carnitine. Carnitine's a big old honking molecule that is a fat transporter in cells, full of carbon-carbon bonds. The chances that carnitine makes it out of your stomach intact is very close to 0. So eat as much carnitine as you want. It's just a hugely expensive food source. It's not adding to your fat transport elements. How am I doing? Now, what's unique about creatine, what makes creatine so interesting, it clearly was part of our ancestral diet. Humans ate tissue with creatine, whether it was insects or fish or meat. We ate a small amount of this. And we have a creatine transporter. Both it is absorbed whole out of the gastrointestinal tract, transported in the blood, and it moves into the target tissue. So, as I said, if you go to GNC, there's probably only one product in 10 that if you put it in your mouth, it actually winds up in the tissue you were hoping it would go to, intact. Well, we should just dance around about creatine because it actually does that. Very unusual. Okay. Now the next step comes is, was the person limited by creatine phosphate in their 15-second performance to begin with? And this is where the theory, Mary, starts to fall apart. If you actually look at studies, whether you look at individual study or you look at individuals within one study, only about half of the people seem to have an effect, meaning roughly half the people may have a limitation of high energy phosphate transfer due to creatine in their 15-second work bout, and a lot of people don't. Remember, Americans eat more meat than anyone else in the world. And so in many ways, what we're eating already is creatine. We already are supplementing creatine phosphate. If someone was a vegan, that's probably the best argument I could, and a vegan discus thrower. Now we're getting into the range. Where's my clinical nutritionist? That would be the range where I would actually think about this. If you had a truly vegan discus thrower or 200-meter runner, well, that might be a reason to really think about creatine phosphate. I will say, because Song and I had a similar, this would be a good one-dog study in the sense that the stuff is safe. It's part of our natural diet. It's almost impossible to overdose on. Right? Has anyone messed with creatine? It's okay to say you've messed with creatine. I want to point out, creatine is not anabolic. It does not drive the synthesis of muscle. If anyone has noticed they gain 2 pounds immediately in the first week, that's water weight. This is an osmotic molecule, wherever it is, and absorbs water. So when it gets into the muscle gains water weight by osmosis. It's not, you can't sit on the couch and expect creatine to make you a better athlete. What creatine will get you, Jermaine?
Question. So if you do lack the creatine, does that mean like the first 15 seconds of your workout, like you won't have enough energy?
It'll be a little lower than it could be if you were optimized in creatine.
It won't really actually affect anything.
No, unless you're a performance athlete, it's absolutely irrelevant. And what will it get the performance athlete? I have to say that what it will get them is an extra rep at the end of the set. Time your set sometime. You'll come out with 1 or 2 extra reps. Or if you're running 200-meter repeats, you'll get 1 extra 200-meter repeat. What is making the muscle improvement? Is it the creatine? No, it's that extra bit of work that the creatine is supporting. So that's really important to realize that if creatine works, and it only works for about half the people, what it's doing is supporting high-intensity work. It's the high-intensity work that's creating the training effect. It's not like steroids where you can sit on the couch and they'll make muscle. Okay? And you'll find that almost all these supplementation beasts are like this, because people are hoping if I drew a circle that represented your entire performance attribute, cognition, strength, power, endurance, and everyone is hoping that these supplements do this. And what only the very best do, most of them do nothing, but the very best do stuff like this. You get a 1% increase in one very highly specific attribute. Do you know what will make your entire circle get bigger? Training. Just a thought. All right, so to finish up, yeah, perfect. So here's where we are. This is a nice overview. That's the blood barrier. Here's the muscle fiber. We've just talked about short-term elements. So here's the, oh, we don't even have the adenyl cyclase reaction on here. So you could put the adenyl cyclase reaction up here. But this and this are immediate stores of high-energy phosphate to resuscitate ATP that is being used up by muscle contraction, calcium ATPase, etc. Next, where we head, and that's tomorrow, so I'm sort of setting you up for tomorrow. Good time to ask questions. Anyone have questions about what we said so far? By the way, if you do try the one-dog study, or anyone else with creatine, the best way to see if it's working is to make some actual measurements in advance. You know, so you load up a weight with 90% of 80% of what you can lift. You do as many repetitions as you can, speed-wise, in 15 seconds. Do that a few times before you start the creatine. Then take the creatine. You know what I mean? If you really want to know if you're doing anything. Subjective feeling is not measurement. That's different. Because the methamphetamine diet works awesome for everybody. You understand how you think. Everyone thinks they're wonderfully better, even after their teeth come out and they're covered in sores. Oh, methamphetamine is great. Dude, you should have made a measurement. Sorry, I hope that's not too hard scientific. So, next we're going to talk about glucose. Notice we have 2 sources of glucose. We are able to break it down in the cytosol and get a small amount of energy, about 3 ATP per glucose molecule. And then, of course, one of the major things you're doing at the end of glycolysis is if you produce pyruvate, you can feed that into the mitochondria. I wish there was a crinkly membrane around this, because these are both mitochondria, so it needs a crinkly crystal membrane. So a few words, and this will help us start better tomorrow. So glycolysis, lysis means breakdown. So glycolysis is the breaking down of glucose or glycogen, once glycogen has been cleaved into a G1P. Glycogenolysis, this would be the lysis of glycogen. So this is the breaking of glucose. This is the breaking of a starch, cleaving the terminal glucose off of a complex glycogen molecule that I think you might look at before we go away. Then gluconeogenesis, the new creation of glucose. The new creation of glucose. So this would be when you take usually two little 3-carbon moieties, like 2 alanines or 2 lactates, or a lactate and alanine, glutamine, and you combine them to make a 6-carbon glucose. So this is the creation of new glucose by the body. This is a rare phenomenon that we have a low maximum capacity to do this, and it generally only happens quite late in exercise. Saul and I were talking about glycogen depletion. This is what your body will try to do every 90 minutes when you're depleted to feed your brain, and it's very unpleasant. You can get better at it, but it's worth it to know that only the liver, perhaps the renal cortex a little bit, can actually make fresh glucose. You know what the body usually does if it needs more glucose? It goes and finds food, driven by a phenomenon called hunger, most common. And then finally, glycogenesis. Well, this was new making of glucose. Glyco seems to refer to glycogen. So glycogenesis is what we do after the workout when we have some carbohydrate food and our muscles, with all those extra GLUT4 receptors installed, are sucking up the glucose rather than us having type 2 diabetes. It's sucking the glucose out of the bloodstream to make fresh glycogen in case you go out and do another workout. Do those words make sense? Okay, they all kind of sound the same the first time you hear them. So kind of break them down. Again, flashcards are very useful for that. So let's look at, I only have 1 slide, 2 slides. Yeah, 2 slides left. I think you're familiar with the concept of carbohydrates. We eat a lot of disaccharides in our diet. There's a lot of natural things. Sucrose, lactose, maltose are very common in what we eat. Monosaccharides are things like fructose, glucose. These are immediately cleaved out of the disaccharides if we eat a simple sugar. And of course, polysaccharide starches, we can't digest fiber from plants, but starches and the carbohydrate in meat can be easily digested out into simple monosaccharides. Everyone's okay with that? For our last figure before we go. This is a really good slide. So what would you call this distance from here to here? I'll give you a hint. This is a muscle cell. So what's the distance from here to here called? This would be the isotropic or light-passing band, as opposed to this darker band that would be called agonist. What's the darkest continuous line in the picture? Yay! When this thing contracts, which way does the Z line go? Yeah? True that? Okay. Then one of the things that we're headed for, the reason I'm showing you, if this cardiac muscle is intensely organized. If skeletal muscle rocks, cardiac muscle is like the aerobic muscle par excellence. And so what you're saying is sarcomeres, end on end, and then these little granules, see all those stippling of little beads? Those are the glycogen molecule that I'll show you a picture of next time chemically. These very white droplets are fat, so triglyceride in the muscle. Dark meat has a lot of fat in the muscle. That's why dark meat is a creamier tasting. If Thanksgiving's coming, you'll figure it out. And the color of the dark meat comes from the high levels of myoglobin, which are an oxygen transporter associated with the mitochondria. So this is just incredible. We use ATP. We make ATP. We use ATP. We make it. It's just a wonderfully set up tissue for high energy output. Remember, the heart is the muscle that never rests, so it's obligated to be pretty organized. Very good.